So we're going to be looking at sections 2 and 3. So we're going to look at dependent samples and independent samples today. Let's go ahead and get started. So our first section 2 material, either chapter 8 or chapter 9, depending upon which class you're in, we're going to be testing the difference between the means with dependent samples. This is also called a paired data. So it comes from something like a pre and post test. So one person is taking two tests or two measurements from the same person, from the same sample item. And then we're comparing the first measurement with the second measurement. And that's how this one will work. And so we need the samples to be dependent, which means they're coming from the same individual. Okay, so the difference between independent samples and dependent samples. The first one of independent samples, so they're selected from one population that is not related to the sample of the second population. So we looked at some of these with seatbelt drivers. Drivers wearing seatbelts, and one was in like Washington State, the other was in Vermont. So they're in completely different states. So samples that come from basically two places that are not, there is no overlap between the two. The second, the dependent samples, not only is there overlap, but the samples are paired or matched, meaning that one sample is measured at one point in time, and then there is another measurement from that same item, from that same person. So this is a pre-test, post-test. And in between, generally what happens is some kind of innovation, some kind of experimental process, maybe a medication. We give them a medication, see if their blood pressure came down, something like that. So that's a pre and post measurement. And another way to take a look at this is that independent samples are not connected. They could actually have different sample sizes because, again, they're independent of each other. It's just a grouping taken from one population and a group from another population, different populations even. In dependent samples, the samples have to have the same sample size because each item, and generally it's a person, but it's not always, each item has a pre-measurement and a post-measurement. If they miss one of these, we can't use them because then we don't have paired data. If they only take the pre-test and they miss the post-test, they're thrown out of the study. Okay, and again, what's happening here is in between there's some kind of a treatment, experimental treatment. Maybe they took a class or took a medicine. Generally is what's going to happen, and we see what happened. We're measuring before and after. Independent samples, it's not that case. It's not. They're just two different populations, and we're comparing what's happening there. Okay, so first one we're going to look at is dependent samples. It's a little bit more complicated, but we're going to look at the sort of the straightforward, simple way of processing these. So first of all, to do a t-test for the difference between means on paired data, three things have to happen. The samples must be randomly selected, so that is pretty much a requirement for all of these tests we're doing, and you'll see that they'll say they're randomly selected. Samples must be dependent, which means that they're paired. There's a pre-test, post-test, a first measurement and a second. Both populations must be normally distributed, or the number of paired data is at least 30. Okay, so that's that magic number. I don't know if magic or not, but anyway, 30 is what we're looking for sample size. If it's 30 or bigger, we can say it's going to have a normal distribution look to it. So then what we're going to do is we're going to get the average, the mean of the differences, and we'll look at that. Basically, we take the pre and the post, and we subtract them, and then that's what we use for our data. We're going to do a t-distribution with n-1 degrees of freedom. Remember, with a t-distribution, we always use one less the sample size. Okay. And then we get a normal look, and then again we get our tails. If our sample will calculate a t-value. If the t-value ends up being, say, in one of the tails, this is the t statistic. In this case, we would reject. But in, say, another case, if, say, the t statistic ended up being here, it's not in the rejection region. For this one, we would fail to reject. Reject. And what we're rejecting always, or not rejecting, is the null hypothesis. If we reject, then we have evidence that the alternative is true. If we fail to reject, we do not have enough evidence. Okay, that's basically how it goes with all of these types of tests. So let's go ahead and see how we would do one. Here's an example coming up soon. So first, what has to happen is we have each data piece, the pairs, the first data and the second data, we subtract them, and that gives us the difference. So let's say you scored 100 on the first test and 125 on the second test. And so the difference is 25. In this case, the way we're doing it, it would be negative 25. Oftentimes they put the x2 first, just depends on which way you want to look at it, as an increase or a decrease. But anyway, you get the difference, and so in this case, d would be equal to negative 25, right? Because it's on that. And then what we do is we add all the differences together, and we divide by the sample size, and that will give us an average of the differences, the mean of the differences between the paired data entries. A lot of verbiage there, but that's what's going to happen. So we get that, and then we're going to also need, so we get the difference. We're going to need the mean of from the hypothesis, and we're going to see this is generally going to be 0, because again the null hypothesis when we have two samples is that there is no difference between the two means. We start with that, and if we can show that there is a difference, then we can see whether it's more or less or just different. Okay. So we get our mean of the differences. Again, add all the differences together, divide by the sample size. We're going to need a standard deviation of these differences, which would be calculated with this formula. And again, you could see, because these differences, what this is doing is it's taking the average difference, subtracting it from each individual difference. So you really need a spreadsheet to do these kind of calculations, or you need something programmed into the calculator that allows you to put in all the data, and it'll do this. But I have been unable to find one in NumWorks or other calculators that has this process set up. So what we're going to do is we're going to rely on these items, the mean of the difference and the standard deviation being given to us, and then we will use the formula from there. And the formula we will use, we'll see in just a moment. Okay, so here's an example. We're asked to test the claim below about the mean of the differences for a population of paired data at the level of significance of alpha. Okay, so alpha here is going to be a 10% significance, and the claim is that the actual population mean difference, remember, is going to be greater than or equal to 0. Okay, and we'll stick with the equal to. So again, we don't have a feature in the NumWorks to set this up directly, but what we can do is we can manually calculate the t-value with this formula. So this is going to be important to have in your notes, ready to use as you go through things. We're going to calculate the t-value, and then we will go from there. We will go to the distributions feature to set it up for us. Okay, so what do we do first? Let's go ahead and calculate this. So we're going to get that t equals d bar, which is negative 2.1, minus the mean of the differences in the population, and we take that from right here, we take it as equal to 0. And again, because we look at the boundary point, and if it, we'll subtract 0. I like that part. Standard deviation, they give us right here, standard deviation of the differences, 1.4, and we divide that by the square root of the sample size, square root of 19. So we put all of this into the calculator. And incidentally, this will be the type of question I'll have you work. We'll do some more like this to prepare us for the exam, but this could easily be the type of question on an exam, just like this. Okay. What we need to do is calculate this, so we'll go into our regular calculator, put a parentheses, negative 2.1 minus 0. Again, you didn't really need to put that minus 0 because it's not going to change it, but I like to match what I've got here. 1.4 divided by the square root of 19. And that's it. We calculate it, and we've got a z-value of negative 6.54. We'll just use 2 decimal places. Will be enough. And remember what this, not a z-value, a t-value. But what we're going to see is when we look at the distribution, a t-distribution, it's supposed to be symmetrical. What we have is this t-value. Remember, this is a value here in the middle. The mean is always 0. So there's a negative 1, a negative 2. So for negative 6 is going to be like way out here, right? So I'm going to say, I bet you we're in the tail, but we've got to figure out where does the tail actually occur. So to do that, we're going to come to our calculator. We're going to use, again, I'll highlight here, this is what we're working with, is this number, is what we're comparing. We're going to use n minus 1 degrees of freedom, so 18 degrees of freedom. We're going to go to our calculator, to the distribution. So we'll go back to the main menu. We'll stay here with distributions, and there's something called the student's t. I'm not sure where the name comes from. It's just instead of a normal distribution, it's our t distribution. Those are similar once we get to 30, a sample size of 30, but our sample size is 19. So degrees of freedom, as it says here, is n minus 1, so we're going to enter 18. So you'll get a slightly different answer for each different degree of freedom. So that's an important input. And then here, what we see our t distribution here. This alpha is equal to 10. What we want to focus on when we're doing these tests is we focus on the alternative. Okay, so what would be the alternative hypothesis? Well, it would be the opposite of being greater than or equal to 0, which means it's going to be less than 0. And it's the difference of the means, and so it's going to be, sort of mean 1 minus mean 2 would be how our calculator puts it in, right? But we're looking for the less than. That's a left tail test. So we did all of this to find out, are we doing a left or a right tail test or something. So we're looking for the left tail. So this is a left tail. What we need to see is what z-value gives us a 10% in the left tail. So not 50%, we'll put in 10% because that's our level of significance. And so this is the setup. Okay, and actually we can do it right here. Our t-value is negative 6.54. This t-value, the sort of the boundary of where you would reject at, is negative 1.33. Well, negative 6.54 is way, like it's, kept going here. There's negative 4. Negative 6 would be like outside the calculator. and we're a little bit further than that. We're 6.5, so we're like, maybe there. So we are definitely in the rejection region, this whole tail, right? So the end result is we use this to say we are going to reject H naught, which is that the mean is greater than or equal to 0, which allows us to say there is evidence that the mean difference is less than 0. So there was a decrease from measure 1 to measure 2. That's what this tells us. And that's good. If we wanted to, maybe as a blood pressure medicine, we wanted to see if our blood pressure medicine actually does reduce the blood pressure, right? This is a good thing. The difference is less than 0 means there was a decrease. We're playing golf and we take a golf class. We want to see if that golf class helps us reduce our golf score. And that, the better you are at golf, the lower the score. Okay, so that's the type of test that you'll need to be able to do for 8.2, 9.2, whatever one you're at. Okay. So now we're going to take a look at section 3, which is the difference between means, and now we're into independent samples. This is going to be very similar to what we did with one mean. We have two different tests. This first one is going to be a z-test because we know the population. So remember, this symbol is for population standard deviation. If we know that, then we use a z-test. If we don't know these, we only know the sample standard deviations. That's what is known. Then we're going to use a t-test. And again, remember, if our sample size is large enough, larger than 30, we could technically come up with very, very close. Sometimes they're a little bit different, but they're supposed to get closer and closer the larger the sample over 30 between a t and a z. But for this purposes, whenever we don't know the population standard deviations, we should be running a t-test. Okay. So let's go into here. This next few slides will be kind of just a review of setting up a hypothesis test. So again, we'll go over it lightly, but these slides I included because they help you maybe remember. Remember, there's always the first one. We set up a null hypothesis. In our calculator, it's always going to be, since we're dealing with two means, that the mean 1 minus mean 2 is equal to 0. That's always the setup in our calculator. We come up with an alternative hypothesis, and that's what we kind of read through the program, the question, to see whether we're doing greater than, less than, or not equal to. Okay, so that's what we do is we'll as we use the calculator, we'll set up the alternative hypothesis as one of these three. So what that does is it means there's really three different tests that we can do that as we set them up. The first one is that mean 1 equals mean 2, or the alternative would be mean 1 is not equal to mean 2. And this would give us a two-tailed test. In our calculator, what that looks like is it shows the means being subtracted. But if you take mean 1 minus mean 2, if it's equal to 0, that's the same thing as saying that they're the same number. Okay, because that's the only way you can take two numbers, subtract them, and get 0. They have to be the same. Okay, and then that makes the alternative hypothesis that when we subtract, that it's not equal to 0, so that the means are different. Okay, so the key word we look for in the question is if it's looking for a difference, not greater or less than, greater than or less than. Those will be the next two ones. Okay, so the next one would be that mean 1 is less than mean 2, less than or equal to mean 2. And the alternative is, notice it's the opposite. Okay, so if we're able to reject the null hypothesis, then we're able to say that we have evidence for the alternative hypothesis. And what that looks like in our calculator is this. This is a right-tailed test. And it's looking at, if we subtract them, again, the null hypothesis is always equal to 0. The alternative in this case is that when we subtract them, this is saying that mean 1 is actually greater than mean 2. So there was a, would have been a, yeah, mean 1 is greater than mean 2. And the last one is a hypothesis that mean 1 is greater than or equal to mean 2. And so the alternative is the opposite. Mean 1 is less than. And what that looks like with our calculators, this is our left-tailed test. And we would see how this looks in our calculator as well, with the alternative being less than 0. So mean 1 is actually bigger than mean 2. So the one we can always sort of use is that the null hypothesis is that there is no difference. So, and again, that's embedded into the calculator itself. So we always start with this as our null hypothesis. So let's go ahead and see what we need for two sample z-test. We are going to calculate the difference between the means. The conditions we need are, we need to know the population standard deviations. We'll emphasize these are coming from the population standard deviation. Samples are random. We talked about that. Samples are also independent. They are not paired. If they're paired, we have to do that paired test. And then that both samples are either normally distributed, this is either or their sample sizes are both above 30. Then we could do this. And then these are the formulas that get used. Fortunately for us in NumWorks, these are embedded into the calculator. So what we're going to do is enter the statistics, the means, the standard deviations that are given, the level of significance, and the calculator will use these formulas to calculate a z-value and then set it up for us in a normal curve because we're dealing with z. Okay, so let's see this one. So we have a credit card watchdog group claims that there is a difference in the mean credit card debts of people in Oklahoma and North Carolina. Is a difference. They didn't say if they're greater or less than, but just that there's a difference. So that's going to be key to setting up our alternative hypothesis. The results of a random survey of 250 people from each state are shown at the left, or actually below. The two samples are independent, okay, so we can use this. Assume that the population standard deviation is 960 in Oklahoma, and population standard deviation is 845 in North Carolina. Do the results support the group's claim? And then we're asked to use a significance level of 5%. Okay, so we're going to put in this data here. We're going to use the standard deviations given to us up here, and we'll run the test. So let's go back to inference. We're going to do a test, hypothesis test, and we're using two means. We'll do either a t-test or a z-test. The one we want to do here is z. We do the z-test whenever we know the population standard deviation. And so we set up this, the null hypothesis always starts with mean 1 minus mean 2 is 0. And so then this one is where we come and we find, now since this question does not say greater than, it does not say less than, it's just saying that there is a difference. That is going to mean that our alternative is going to be not equal to 0, which gives us a two-tailed test. Okay, so it's going to be a two-tailed test. We're going to input our statistics. And so we put in mean 1, which is 5,271. We put in the population standard deviation for 1, which is 960. And then we put the sample size for 1, which is 250. Okay, so this is just like using a formula. We're plugging numbers in, but into the right places here. The calculator then takes those and plugs them into the formula for us and does the calculation. Mean for North Carolina for sample 2 is 5,121. Again, which is different than Oklahoma, but remember we're trying to see, because these are samples, we're just trying to see if there's really a population difference or not. Standard deviation is 845 for population 2, and the sample size for population from population 2 is 250. And then this is where we put in our level of significance, which is 0.05. That's the default, so we can just accept that. Then we're going to get all our calculations. We got a z-score of 1.866. We'll see how we can compare that later. But what we can compare right here is that we've got a p-value of 0.06. So we compare the p-value to the alpha value, 0.62, and we see that p is greater than the alpha. 6% is bigger than 5%. And so we hopefully can see that at this point we are going to fail to reject. And if we want, we go to the next level on the calculator and it will show us the normal curve and it'll show us the rejection region, and we'll see that our p-value is outside of the rejection region. And again, we have to focus in on one of these. And we see that the rejection region has these hash bar marks or stripes. Let's go with the red. And so the rejection is right here and back if we need to be in there. And notice our p-value takes us over here. We're outside of the rejection region. And that happens, it was a two-tailed test, so if you click over here, the same thing is going to happen. We are outside of the rejection region, which would be, again, here is the rejection region. This is where our z-value is. We're outside of that rejection region. So we fail to reject. We do not have enough evidence to say there is a difference. That's it. Okay. And what we'll do now is we'll walk through. I left these slides in. This is how the textbook company sort of worked through it. Notice the claim that we came up with is correct. They had to go and look up the z critical values, which the calculator did for us. It didn't really actually tell us what those z critical values are, did it? It doesn't. It shows us here, and it's showing us that our result is bigger than that. So when we use the calculator, we're particularly focusing on the p-value and the alpha value. Okay, here they get the actual z-values, and that's the marker for a 5% test, right? 95% in the middle. They did the formula, and notice the formula comes up with the same z-value that we did. There's a little different. Sample z-test, am I doing the right test? I'm doing a z-test. Should be 1.866, so maybe they have a rounding error, I would assume. But we're pretty close. I didn't look at that as closely as maybe I should have. So it looks like there's some sort of a rounding error, but these values should be the same. Let me just back up and make sure I've got all my statistics in correctly. 5271, 960, 250. I'm off by 1. See, somebody was off. I knew we should have exactly the same value. So 5121, I put in 5120. Not enough to make a big difference, but you know, it's it would have been marked wrong by the homework system, right? 845. So just being off by that 1, we'll go to the next, and now our numbers match. So sorry about that. Sorry, textbook said you were wrong when actually I was wrong, right? So just be careful, check on things. And again, a lot of times I just get going on things and I always assume I'm right, but it's so easy to enter something in incorrectly. So do that double check. And then again, they show the same picture sort of we saw, is that once you go through, you can see where the rejection region is. We have to kind of zoom on that, and that the rejection is outside of. So it's on the right-hand tail. It's outside of the right-hand tail here at 1.85 versus 1.96. We see the same thing with our calculator. One more example, and then we'll call it a day. The other thing you can do is as you click through here, this helps you to see the wording that you would use. If we fail to reject, there is not enough evidence. That's the key I'm looking for. If you can just remember, hey, P is P is greater than alpha, right? The Z's outside. We're not in the rejection region, let's put it that way. We're going to fail to reject, so there's not enough evidence. If you tie those two things together, that is the lesson I want you to learn, because you will carry that with you. If we do reject, then there is evidence, and there is enough evidence. So those are the two things that always go together. Fail to reject with not enough evidence, and reject with enough evidence. Okay. So that's the hypothesis test here. We'll look at one more example, and we'll do this, and then we'll call it a day and let you get working on the homework. So a rental market researcher claims that the average monthly rent for a one-bedroom apartment in Seattle, Washington is less than the average monthly rent for a one-bedroom apartment in Washington, D.C. This is going to help us set up the hypothesis test, less than. So less than looks like that. The table at the left or below shows the results of a random survey. So again, that's important that it's random, who rent apartments in each city. The two samples are independent. And then we're told to assume a standard deviation, population standard deviation of 190 for Seattle, population standard deviation of 210 for Washington, D.C. We're told that both are normally distributed, which is important. Not so important because the sample sizes are both over 30, but that's helpful. And then we're asked to test at the 0.01 level, the 1% level, if there is enough evidence. Okay. So again, we go to our hypothesis test. Go back far enough. Tests, two means. We're going to do a z-test because we know the population standard deviation. We're going to set up the hypothesis test. The null hypothesis is always equal to 0. The alternative in this case is telling us this is where that comes in, that we're going to go with less than. So it'll be a left tail test. And then we're going to input our statistics. In this case, 2,166 for the rent in Seattle. The standard deviation is $190. That's a plus or minus. And then the N1 sample size is 400 people, 400 apartments, 400 rental units. Sample mean in Washington, D.C. is 2,181. And I'll be a little bit more careful to make sure I get it correct. Sample size, standard deviation is $210. We got that. And then our sample size is 300. Level of significance is 1%, so we put in 0.01. Go to next, and now we can compare the p-value. So we were given a 0.01. I'll write that over here just so I have room. And our p-value is 0.165. 16.5% is much bigger than 1%. P is greater than alpha. We fail to reject. So we know there's not enough evidence. Again, we can see that when we come to the next. It is a left tail test for sure. You don't have to zoom too much, but we are way outside of the rejection region. Rejection region cuts off here, and look where we're at over here. We are outside of this rejection region of this tail, right? This is where we would reject. This is the unusual. We are in the usual territory, so we can reject it. Now, we can't say that they're different or the less, we can't really say anything. We just do not have enough evidence to say that the rents in Seattle are less than the rents in Washington, D.C. We don't have that evidence. We can't say they aren't. We can't say they are. We can't really say anything. But that's the hypothesis test. Okay, and I think I've got one more slide. Here's helping us out. So they get their Z statistic. The rejection region's negative 2.33. Their statistics negative 0.7. So yeah, you kind of see here, this is, yeah, looks like about negative 2.33. We're right about negative 1. So we are not in that rejection region. Fail to reject. And when you fail to reject, there is not enough evidence. That's all we can say. And that's it. So now you're ready to work through the homeworks in sections 1 and 3, or sorry, 2 and 3. And then we'll take a look. One more thing is when we do a t-test, and we'll take a look at that in the next section.